So today's note card is basically just going to kind of build off of note cards 62 and 63, which was disc and washer method. Really the difference today is we're going to be doing volume of axis other than the X or Y axis. So if it's spinning around another vertical or horizontal line besides the X or the Y axis. So overall the strategy is going to be pretty similar. You're still going to want to draw a picture of what the region looks like. You're going to decide whether we're doing a DX. So if it's a horizontal rotation, just a reminder, remember horizontal line is when it's Y equals a number. Or if it's dy, because it's a vertical rotation, again, remember the equation of a vertical line is actually x equals a number. So if it's going around y equals a number, it's actually a horizontal rotation, and if it's x equals a number, it's a vertical rotation. And then determine whether we're going to be doing disc method or washer method. That basically has to do with whether the area is flush up against or touching the axis the whole time. That'll determine whether or not there's a hole in the middle or if it's a solid shape. We're then going to, as always, do the limits of integration, either based on the directions or the intersection points. So then the big kind of key piece for this one is then we're going to want to go ahead and draw or label big R, which big R is going to be the radius from the axis of revolution, what we're spinning around, to whatever function is furthest from the axis. And then your little r is going to be the distance from the axis to whatever function is closest to the axis. And the difference between this and just regular disc method is the idea that big R and little r are going to be binomials this time. Meaning that it's not just going to have one function, it's going to have typically a function plus or minus a number. If it's dx, it's always going to be that t minus b stands for top minus bottom, if it's dx. Or if it's doing a vertical, it's always going to be whatever's on the right side minus whatever's on the left side, if it's dy. So let's go ahead and look at a few examples. So the first one, this is a calculator active. It says let R be the region enclosed by y equals square root of x minus 1, the vertical line x equals 10, and the x-axis. Find the volume of the solid generated when R is revolved around the horizontal line y equals 3. So remember, if we're spinning around a horizontal axis, that's going to be more like doing around the x-axis. So that's going to be a dx because it's a horizontal line. So let's try and kind of sketch out a picture of what our region looks like. So our function, the root x minus 1, that would basically just be the square root function but shifted right by 1. So it kind of would start at 1 and then kind of just go up and to the right like that. So that would be the root x minus 1. The line x equals 10 is just going to cut off the right side. And the x-axis is going to form the bottom. So to clarify, the area we're interested in would be the entire area sort of inside of all those. So under the square root, left of the vertical line, above the x-axis. That's the area we're interested in. So the difference is that instead of spinning it around the x-axis or the y-axis, we're spinning it around the line y equals 3. What might be kind of helpful to do real quickly to sort of know where that's going to fall is let's look at the far right corner of that square root function. What would be the y value at that point? If we actually plug in 10 to the square root of x minus 1. So that becomes square root of 10 minus 1, which would be square root of 9, which is actually 3. So that is actually already at a height of 3, that graph on the far edge there. So now if I kind of sketch in my axis, So my axis, we are spinning around the horizontal line y equals 3. So basically on the far right corner of the blue region, we're actually touching the axis. Everywhere else, we have this white empty space. So this area here, that white empty space tells me that this is going to be a washer method because the blue area is not touching the axis that whole way, the line y equals 3. So that's our hint that this one is washer method versus disk method, because of the fact that there'd be that gap. So I think we have all the other pieces we need. We know where we're going to start and end on the x-axis. We know which functions close it off. So now we can kind of set up our pieces. So the big R is going to be the distance from between the axis and the function further away. And it's always going to be whatever's on top minus whatever's on the bottom. So in this case, the thing on top is the axis. And in this particular one, the thing on the bottom is basically just the x-axis. So notice I drew my arrow sort of starting at the top, going towards the bottom. So my big R in this case is going to be whatever was on top first, so 3, minus the bottom, which is just the x-axis of 0. So essentially, my big R is actually just going to be 3. Now, my little r is going to be the distance from the axis down to whatever part of the graph is closer to the axis. So in this case, it's going to be the distance from the axis, which is above, down to the curve. So little r is going to be 3, axis first, because it's on top, minus the function, root x minus 1. And then that actually can't simplify any further because of the root. So that would be my little r. So now we have all the pieces we need. So this one, we just need to set it up by hand, and then we'll do the rest in the calculator. So volume, we still have pi because we're spinning. It's going to be the integral from 1 to 10 of, we want to kind of remember it's big R squared minus little r squared. So in this case, big R is going to be that purple guy, so 3 squared, minus little r, which is the green guy, 3 minus root x minus 1, all squared, and then everything dx. So that's my setup. You don't have to clarify. You don't have to write the big R, little r on top. That can sometimes just kind of help people label to remember. Like the 3 is the big R squared, the green part's the little r squared, and we're minusing. So then from there, if this is calc allowed, you can now just type the rest of that in the calculator. You just kind of want to make sure we're being careful in terms of our brackets and our parentheses. So don't forget to put your pi out front. And then it'll be the integral from 1 to 10. And then inside 3 squared minus parentheses 3 minus root x minus 1. Get out of the root, close parentheses, squared, don't forget the extra squared, and then dx. It might take the calculator kind of a minute to think about it, but I'm coming out with 212.058. So if you want to kind of pause here for a minute and see if people can get to that point and check in. And then when you're ready, you can go on to example 2. All right, so example 2, it doesn't really specify, but we can go ahead and also kind of, the homework on this is all going to be calc loud, so we can probably just assume once we set it up, we can finish this one on a calculator. So here we have region R in the first quadrant only is enclosed by y equals x cubed, y equals the cube root of x, and we're looking for the volume found by revolving this region about the line x equals -2, which to clarify, that is actually a vertical line, which means this one's going to be a dy, where we're spinning it around a vertical axis. So let's try and kind of sketch a little picture here. So we mostly want to do in the first quadrant, but we want to leave a little room because notice our axis over here, x equals -2, that is the line we're spinning around, the line x equals -2. So then the graphs, let's think about our graphs. So we have y equals x cubed, so that would just be kind of our normal cubic function. And then we have y equals the cube root of x, which if you don't remember is basically just the sideways cubic function. That kind of goes, it'll be concave up on the right, cross at 0, concave down to the left. So they actually kind of intersect twice, but it was only interested in the region in the first quadrant. So we only care about that little area. That would be the region R. So we need a little more information to set up our pieces. We can go ahead and think about our limits of integration. So the bottom of that area on the y-axis looks like it's 0. Both of those would intersect at 0. The top of that area on the y-axis, you could do it kind of mathematically, but if we just sort of think in our heads, there's only one other number where cubing something and cube rooting will give us the same answer, and that would be the number 1. So that's our limits from 0 to 1. And let's go and set up our big R and little r. So the big R is going to be the distance between the axis and whatever graph is further from the axis. In this case, the one further from the axis will be the blue cubic graph. And then notice I'm going to draw my arrow in the direction that we want to do our math, which is going to be right side first, blue graph, heading left towards the axis. So then my big R, because we're doing vertical, we're thinking right minus left instead of top minus bottom. So in this case, think about what is on the right side. The right side is going to be the actual graph. The left side is going to be the axis. Now, one other thing we want to be careful of, remember we said a minute ago this is dy. So right now, I need those equations to be rewritten in x equals y format. Let's do that real quick. So this first guy, y equals x cubed, if we rearrange it, would just become x equals the cube root of y. And the other one, y equals cube root of x, if we cube both sides, would just become x equals y cubed. So they're kind of almost going to just flip spots. So the blue one would actually become x equals cube root of y, and the green one would become x equals y cubed. So then my big R is going to be the blue graph rearranged. So cube root of y minus the axis, which is -2. So now because the axis is a negative number, instead of doing minus minus -2, I can go ahead and just rewrite that as cube root of y plus 2. So that's my big R. Now my little r is going to be the distance from the axis to the graph that's closer, which is the green one. But notice my arrow, I'm starting on the right, heading towards the left. So my little r is going to be whatever was on the right side, which is the green graph, y cubed first, minus the axis, which is -2. And then similar, that would just simplify to y cubed plus 2. So that's my little r. Now I think we have all the pieces to assemble our volume. So my volume is going to be pi integral, remember our limits were 0 to 1, and then it's going to be big R squared, which will be cube root of y plus 2 all squared, minus little r squared, which is y cubed plus 2 all squared, and then at the very back, dy. And then because this is Calc Aloud, we can go ahead and evaluate that on the calculator. Remember, when you're typing it, you can go ahead and just put x's for the variables instead of y's. Don't forget to put the pi out front. So we're going 0 to 1. Be really careful of the parentheses. So parentheses, cube root of y. Remember, you find that under the math menu, option 4. So cube root of x plus 2, parentheses, squared, minus extra parentheses, x cubed plus 2. Close parentheses, squared, and then all dx. And that equals 7.719. So again, if you'd like to kind of pause here for a minute, give everyone a chance to try that calculator piece, see if you all get the same result or need any help. And then when you're ready, you can go ahead and hit play and we'll look at a couple of the examples in the back.